All right, so here we're going to take a look at, we're going to start the laws of Boolean algebra. All right. So first of all, what is an algebra, right? So we know ordinary algebra, operations of addition and multiplications, and identities like distribution. Right, we know that xy plus xz. All right, now when we talk about Boolean algebra, okay, our variables aren't representing uh, real numbers or just numbers in general. Our variables represent propositions with values that are true or false. All right. So here, when we have, let's say, p, right, the value here can be true or false. Right, and we have operators that are like and, or, and then the negation operator. Right, and our logical equivalents hold for all true and false assignments. Right, so now another thing that'll be different here is that instead of using equality, what we'll use is this 3 symbol here. All right, there are equivalents, right, when they agree for every possible truth value statement. All right, so again, named after George Boole, this Boolean algebra here. So let's just start with some basic ones, right? Some of our Boolean algebra laws, some pretty obvious ones. Part 1 here, the double negation. So here, if we negate not p, right, that is equivalent to p. All right, so here, p can be either true or false, right? Not p. If p is true, not p is false. If p is false, not p is true, right? That is the duality of these statements, right? Well, what if I negate the negation? All right, not p. So if not p is false, not p would be true here, and if not p is true, the negation of that would be false. And then we see here equivalent truth tables. Hence, we have that equivalence relationship. Okay. All right. So here, what's called the excluded middle. If we have a statement like p or not p, well, this is just going to be true. Right, it's equivalent to something that is true. Every proposition is either true or false. There's no middle ground, right? And again, think of our or table, just looking at this out here. If we are going to include p or not p, only one of them has to be true. And we see at each step, right, that would be true when we say or. All right, and on the other side of that, the contradiction, when we state p and not p, right, well, this will always be false. Right, now for this one, right, p and not p, we need both to be true, right, and that never happens, right? So that's false, that's false. All right, a proposition and its negation cannot be both true, right? Because each of these propositions is either true or false. It cannot be both. All right, now some identity laws here. Okay, so our identities say true and p is always equivalent to p, right? And then false or P, that's always equivalent to P. Right? If we already know that Q is false, then P or F has the same value as P. Okay? All right. Now the what's called the idempotent laws. Right? So for these we state P or P. Well, yeah, that's always equivalent to P. Right? And the same for P and P. Right? That's just logically equivalent to P as well. All right. Now, these laws are also commutative, in other words, that the order does not matter. Commutative, right? Right, so for this one, we could say P and Q, logically equivalent to Q and P. Right? And then P or Q, right, logically equivalent to Q or P. All right. Now our associative laws. Now these only work when we have the same kind of operator. So just be mindful. All right. So our associative laws state P and Q, P or Q or R is logically equivalent to P or Q or R. Right? And the same works vice versa for the and, right? For our associative and. P and Q and R. All right. And that is P logically equivalent as P and Q and R. Okay. All right. So those are just our basic ones. All right. We also have more that are more interesting. They're more powerful, I guess, because it allows us to kind of look at these operators across mixing and or, and how do we work with those, right? So let's start with the distributive, our distributive property. Right, so now this one states here, we have P or Q and R is logically equivalent here to P or Q and P or R. And at the same, or the other one, the dual one, the pair that's attached to it is P and Q or R. Q or R is logically equivalent to P and Q or P and R. All right. All right, so again, a language example, we could say that this card is the ace of spades. Or clubs. All right. So here we say letting A be the ace, S be the spade, and then C be the club. So we have A and, right? So it's the ace and S or C, right? So that's logically equivalent to saying I have the ace of spades, so it's an ace and it's a spade, or it's an ace and it's a club. Okay, so a way to think of these, the distributive laws. All right. So again, be careful we don't mix these up here. Right. We have the and distributes over or, and or distributes over and. All right. And again, now this is different than our algebra where we distribute multiplication over addition, but not the other way around. So again, just a difference there. Okay. All right. And then lastly, we have De Morgan's laws, which we talked about earlier in the semester. Yeah, so De Morgan's laws also follow this Boolean algebra. We talked about in relevance to sets here, but they have their equivalent Boolean algebra here. So P and Q is logically equivalent to not P or not Q. Okay. And here, not P or Q is logically equivalent to not P and not Q. All right. Okay. All right. Okay, so common mistake here, as always, is forgetting to flip around your operator symbol, right? Going from or to and, or vice versa. Right? So just be careful, right? Keep these in mind here. All right, so just have a basic understanding of knowing all these groups of laws. Okay, laws can be applied in either direction, hence why they are equivalents. Equivalences.